So this lesson is on finding derivatives of inverse trig functions. So our goal for the first problem is going to be to find the derivative with respect to x of the inverse sine of x, or equivalently, the derivative with respect to x of the arc sine of x, depending on the notation that you use. And we're going to use an implicit derivative to do that. So here's our strategy. Y is going to be the inverse sine of x. And again, our goal is to find dy dx. That's the derivative of y with respect to x. That will be the answer to our question. Now, how am I going to do this? You could memorize that form, but I think it's more helpful to see where it comes from. If y is the inverse sine of x, that means the sine of y equals x. That's in essence our definition. Then we take the derivative with respect to x of sine y equals the derivative with respect to x of x. Now, what is the derivative with respect to x of sine y? Let's talk about that. The derivative with respect to x of sine y. That's what we want. The way I'm going to think about this is I'm going to say the derivative with respect to x of sine something is cos something times the derivative with respect to x of that something. So the derivative with respect to x of sine y is cos y times the derivative with respect to x of y. So what we get then is the derivative with respect to x of sine y is cos y times, now let's think about this. What is the derivative with respect to x of y? That is dy dx. That's what we're going to try to find out. So here now we have the derivative with respect to x of sine y is the derivative with respect to x of x. We've just done this. The derivative with respect to x of sine y is cos y dy dx. Equals the derivative with respect to x of x, which is just 1. Remember, our goal is to find dy dx. So we're going to divide both sides by dy dx. Dy dx is 1 over cos y. But I'm not finished because I need to do all this in terms of x. I need to do this in terms of x. And the way I'm going to do this is I'm going to recognize a couple things here. I know that sine of y is x. If sine of y is x, can I figure out what cos of y is? Well, we have one of our favorite identities, which is, of course, cos squared theta plus sine squared theta is 1. So changing the variables, then I could say cos squared y plus sine squared y is 1. Well, what are we saying? We're saying sine of y is x, so sine squared y is sine y times sine y, would be x squared. Just so you're clear. Cos squared y plus sine of y squared equals 1. That's what that notation means. Then we would say cos squared y plus x squared equals 1. So then what is cos squared y? Cos squared y is 1 minus x squared. So then cos y is either positive or negative, and for the sake of discussion, let's just go ahead and call it the positive version. And there's reasons we can do that. Cosine of y then is the square root of 1 minus x squared. And that finishes my question, because remember over here we said dy dx was 1 divided by cosine of y. I've rewritten that in terms of x to say dy dx is 1 over cosine of y is the square root of 1 minus x squared. So my conclusion then is the derivative of inverse sine of x. My conclusion would be to say that the derivative with respect to x of the inverse sine of x is 1 over the square root of 1 minus x squared. Now I'd like to check that. And you know I can check that on the graphing calculator or on Desmos. So let's see if that's what we get. So let me quickly pull up the graphing calculator maybe, and then we'll see what that looks like. So here we go. Graphing calculator is here, and I want to look at the derivative of inverse sine of x. Make sure you are in radian mode. Mode radian is good. Y equals inverse sine, which you'll notice is here. Second sine is inverse sine of x. And I want to take a look at its derivative. How do I graph its derivative? Math, numerical derivative, with respect to x, of my function is y1, vars, y vars, y1, at every point x. I'm going to turn off the function, which is blue, and the derivative is red, and we'll see what that looks like. Zoom decimal. This is what the derivative of the inverse sine function looks like. What do I believe it is? I believe it's 1 over the square root of 1 minus x squared. Do I get that when I plug that into the calculator? So notice the derivative of inverse sine is red. Let me turn that one off. And I will instead graph what I think the answer is, 1 divided by the square root. Oh, that's not quite right. 1 divided by the square root of 1 minus x squared. Get rid of this thing. And now let's go ahead and graph that. That'll be black. Is that the same thing we had with red? If we turn red back on, you will notice that it graphs on top of the black function. So that's a pretty good indication that it's correct. So let's remind ourselves of this process one more time, just to see how it works all the way through. So we started with what? We started with the inverse sine of x. We wanted to rewrite that. How did I rewrite that? Y is the inverse sine of x is equivalent to sine of y equals x. And my goal was to find dy dx, that's the derivative of y with respect to x of this, which would be the same thing as dy dx for this. What did I do next? Took the derivative with respect to x of both sides. The derivative with respect to x of x is just 1, no problem. The derivative with respect to x of sine y, that required a little work, right? The derivative of the sine of something is cos of something times the derivative of the something. So the derivative with respect to x of sine y was cos y dy dx here. Now notice this enabled me to solve for dy dx, just dividing both sides by cos y. And many students think this is the final answer, but not really, because x is our independent variable. So we need to go ahead and rewrite cos y in terms of x. And we did that with our favorite identity, cos squared theta plus sine squared theta is 1. Replace theta with y, cos squared y plus sine squared y is 1. Sine squared y just means sine y squared, but we said sine of y is x, so replace sine y squared with x squared. Now I have cos squared y plus x squared is 1. So cos squared y is 1 minus x squared. So cos y is either positive or negative, but the way that we define it will always be positive in terms of the domain and range of the inverse function. So cosine of y is going to be root 1 minus x squared. Then I replace cos y with root 1 minus x squared. That's our process. So let's do another one. Again, using an implicit derivative to find the derivative of an inverse trig function. This time I want to find the derivative with respect to x of the inverse tangent of 3x. So let's repeat that process. So y is the inverse tangent of 3x, and our goal is to find dy dx. Y is the inverse tangent of 3x. What does that mean? That means tangent of y equals 3x. Then we want to take the derivative with respect to x of both sides. The derivative with respect to x of tangent y, that'll be a little bit of work. The derivative with respect to x of 3x, that's pretty straightforward. So how do we do the derivative with respect to x of tangent y? The derivative with respect to x of tangent y. Remember, the derivative of tangent of something is secant squared something times the derivative of the something. We write that down. The derivative of tangent something is secant squared something times the derivative, in this case d dx, the derivative of the something. But our something here is y. So the derivative with respect to x of tangent y is secant squared y times the derivative with respect to x of y, which is dy dx, and that is what I want to use. That is what I want to solve for. So as I make the substitution now, the derivative with respect to x of tangent y is secant squared y dy dx. Equals the derivative with respect to x of 3x is just 3. So now what am I going to say? We can divide both sides by secant squared y, and I could say dy dx is 3 divided by secant squared y, which is the same as 3 times secant y quantity squared. And let's do some work here. And what I'm going to do this time is I'm going to use the fact that tangent of y equals 3x to do some work with triangles. So we're told tangent of y is 3x, but it's really 3x over 1. But you also know tangent is opposite over adjacent. So knowing that, I can draw a triangle. Tangent y. Opposite is 3x. Adjacent is 1. How do I get the hypotenuse c? What do we know? Well, we know a squared plus b squared is c squared. So we know 3x squared plus 1 squared is c squared. 9x squared plus 1 is c squared. So c is plus or minus, but the way we have it drawn, it's got to be positive. The square root of 9x squared plus 1 is c. Okay, that's nice to know. But I need secant squared. So how do I get secant? Secant is the reciprocal of cosine. So knowing that, cosine of y is adjacent over hypotenuse is 1 over square root of 9x squared plus 1. So secant y, reciprocal of cosine is secant. So secant y is square root of 9x squared plus 1. Now square both sides. Secant squared y equals 9x squared plus 1. All right, so making that substitution, dy dx, the derivative of inverse tangent of 3x should be 3 divided by that. Coming back here, dy dx is 3 divided by secant squared y, 3 divided by 9x squared plus 1. So my conclusion to this then is the derivative with respect to x of the inverse tangent of 3x is 3 over 9x squared plus 1. That's what we believe the final answer is. which I would very much like to check on the graphing calculator. So what I'm going to do is I'm going to look at the derivative of inverse tangent of 3x and see if it indeed is 3 over 9x squared plus 1. So again, I am in radian mode. This time I want to take a look at the inverse tangent. So you see that here. Whoops, put it in y1. Inverse tangent of 3x. And I want to graph its derivative. So math, numerical derivative is number 8. The derivative with respect to x of y1 at every point x. I will turn off the blue function and just look at its derivative. Zoom decimal maybe. And that's what the derivative of the inverse tangent of 3x looks like. Now I believe that that should be the same as what? As 3 over 9x squared plus 1. Let's see if that's the case. So I come back here. We will now turn off the derivative of inverse tangent 3x. And let's see if it is the same as 3 over 9x squared plus 1. 3 over parentheses 9x squared plus 1. And we'll graph that now. Is that the same as what we had before? So we'll turn them both on. We'll turn on the red graph, the derivative, see if it matches the black graph, what we think is our answer. And does the red graph on top of the black graph? And sure enough, it does. So let's quickly do one more. This time our goal is to look at the derivative of the inverse secant, say of 2x. So that's our goal. The derivative with respect to x of the inverse secant of 2x, that's our goal. So we're going to say y equals inverse secant 2x, and our goal is to find dy dx. That's the derivative of that function. If that's the case, then secant of y equals 2x. That's what it means. Then we're going to take the derivative with respect to x of both sides. The derivative with respect to x of sec y equals the derivative with respect to x of 2x. Now what do we know? We know the derivative with respect to theta of sec theta is sec theta tan theta. So the derivative with respect to x of sec something is sec something tan something times the derivative of the something, thanks to this chain rule. Sec something tan something times the derivative with respect to x of the something. But what is our something here? Our something here is just y. So we wind up with then the derivative with respect to x of secant y equals sec y tan y times the derivative with respect to x of y, which is just dy dx. So we make that substitution here. The derivative with respect to x of sec y is this, sec y tan y dy dx. Equals the derivative with respect to x of 2x, which of course is just 2. And then how do I finish this? I finish this by saying dy dx is 2 over sec y tan y. But I guess I'm not really finished, am I? Because I need to get my final answer in terms of x, not in terms of y. So what do I know? What do I know? I know this. I know secant of y is 2x. Secant is reciprocal of cosine. So cosine of y is 1 over 2x. But I also know cosine of y is adjacent over hypotenuse. So we draw a triangle. Here's y. The adjacent is 1. The hypotenuse is 2x. I need to find the third side, which for the sake of discussion, I will just call b. And then using Pythagoras, what can I say? B squared plus 1 squared is 2x squared. B squared plus 1 is 4x squared. B squared is 4x squared minus 1. And the way we define this, these things are positive. B is going to be the square root of 4x squared minus 1. So that's B. B is the square root of 4x squared minus 1. Now, what is secant y and what is tangent y? Well, secant y we already know. Secant y is 2x. So I can go ahead and make that substitution. And dy dx, which is my derivative of inverse secant of 2x. Secant y is 2x, fine. But I could also get it from hypotenuse over adjacent, which is the flip of adjacent over hypotenuse. Now, how about tangent y? Tangent y is opposite over adjacent. So tangent y is b over 1. So tangent y is what we just figured out here. Tangent y is the square root of 4x squared minus 1. So replacing tangent y with the square root of 4x squared minus 1, we get this. And then, of course, we can divide out those 2's. So my final answer, the derivative of the inverse secant of 2x, which was our dy dx. The 2 and the 2 divide out, and we get 1 over x, maybe absolute value of x if you want. We don't have to be quite that formal, because x has to be a positive number for this to make sense. And that's what we get for our derivative of the inverse secant of 2x.